Jesus story, actually, that's the first time I heard about it is from your email because I'm not from a Western background. But it's really interesting because in China, we also associate stars with special events.
Thank you, Munan, for coming. We
Thank
brought
you.
you in so that we could discuss about stars because it's approaching Christmas. Merry Christmas, everyone.
Merry Christmas!
In many Christmas stories around the world, there is always a reference to light. And in the Christian story, Jesus is announced by the arrival of a star in the sky. What does it mean to have a star appearing in the sky?
Jesus story, actually, that's the first time I heard about it is from your email because I'm not from a Western background. But it's really interesting because in China, we also associate stars with special events. For example, if somebody who's important died, we will see the star falling from the sky a day before. So it's seen as a prophet, like in the Western culture, somewhat similar. So we're trying to connect important events on Earth to what's happening in the heaven. But of course, we don't think physically there is a connection, but people like to make a cultural association. Especially in the old times, we don't quite understand why stars appear in the sky and how they work and what they are. I think nowadays, we know how stars form and planets form. We still are trying to make connections and trying to find, for example, signatures of life in other parts of the universe. So sort of the cultural background. And what it is, I think there are mainly two theories. We're not quite sure. We know that most of stars in the sky are fixed. That's because the stars, although they move in the galaxy, they don't move at a very fast rate and they're very far away from us. So it's like, when we take a train and things move outside of our window, but for things really was very far away, a few kilometers, like the mountains, we don't see it moving very much, although the train is moving. Mm-hmm. So the stars do move, they do change positions, but we don't perceive it unless we have a very accurate telescope. What happens, sometimes we have these objects that are not fixed, they're transient objects. For example, one can have new stars forming. One can also have stars dying in parts of the galaxy, and one can have things happen in the solar system. For example, we can have comets that coming from the outer solar system to the inner solar system. And the main two things that could have been bright enough for people to observe with their eyes without the help of the telescope in the ancient times, there's two very obvious objects, and one is what we call a supernova. So these are stars that are dying. So at the end of their life, some of the stars, usually stars that are more massive than our own sun, will explode. And this explosion, they will release a lot of energy. So for some period of time, brightness of the star will be more than the brightness of the whole galaxy sometimes. So it's a very violent event. And that can appear for a short period of time, be a very bright object in the sky. This explosion, happens in a short period of time and the energy is released and radiated away. After a few days, usually the light will fade. So we'll see this event to be, emergence of a new star. That's the supernova assumption. So this assumption seemed to fit the story. But the problem is that we haven't found any supernova remnants. So supernovas also leave behind what we call remnants, or basically gas. We haven't found supernova remnants that nearby that matches the time of the birth of Jesus as described in the Bible. So that could be a possibility. And the other possibility, a leading theory, is a comet. So comets are basically snowballs. They're made of dust and ice in the outer solar system. They're very far away, so even beyond Pluto. Sometimes they would come in and then they will approach the sun. And when they approach the sun, then maybe it will be close enough to us that we can see them. Some comets that we can predict when they come back, for example, the Halley comet. However, there are many comets that just come back once or come back every tens of thousands of years that we cannot predict. So it could have well-being comet that appeared in the sky that people could perceive it as a new star, a new object. So these are the two leading theories of what's happening astronomically. Of course, we don't have any proof. Likely we're not ever going to figure out what's the actual event, but these are basically the theories from astronomers.
So we still don't know. You said if it was an explosion, then we should see some...
We should see some remnants.
Some leftovers. How do you find these remnants?
So the remnants will also glow. For example, there was one of the brightest ones. This supernova exploded about 1,000 years ago and then formed what we call the Crab Nebula. So nebula is basically a hot ball of gas, and because it's hot and they also have some energy from some radioactive decay of the elements that's made in the explosion, then you can see it glowing. So actually Crab Nebula you can see with a very small telescope. I've seen it with my own eyes through a small telescope. And then there's some further away supernova remnants that you might need help from larger telescope in order to see them. So these are the aftermath of supernova explosion. So during the explosion, so ideally you want to catch the supernova explosion before and after it's exploded. These events are relatively rare in the galaxy close to our own sun. What astronomers do is that they study stars in other galaxies. So we take pictures of these galaxies over time, and sometimes we'll see this very bright star. If you take the picture of the galaxy over time, so you can study, for example, the property of the supernova.
If a star takes just a few days to die, well, at least the supernova
maybe a little bit longer, tens of days, but not super long, not like years.
How long does it take to be born, a star?
Even longer. It takes about millions of years to be born, depending on how you count, depending on where do you count as the start of the star. So we know the star is born. The time at the point when the star is born is when we define it as a point that nuclear fusion starts to happen. So when the center of the stars is hot enough and triggers nuclear fusion, then we think that's, time zero, the star is born. But usually what astronomers do is to come back to the stage what we call dense molecular cloud. Call them clouds, but it's basically gas and dust. So if you look at the Milky Way, you will see some dark patches in the Milky Way, so that block the starlight. So these are the dense molecular clouds because they have so much dust, acts like a fog, and it blocks the starlight from the background star, so you can actually see with your own eyes in a very dark night sky. So these are dense molecular clouds, and then we think that the stars are born within them. So in order for the stars actually to form, you need this gas to collapse under gravity. And gravity is always acting in one direction. It always attracts matter. So that's why it's such a powerful force. Even though what we call the dense molecular cloud, they're very, very diffuse compared to the gas on Earth. But because the whole galaxy is so big, the size of the molecular cloud is so big, and the gravity is always pulling one direction. So it takes just a really, really long time for the gravity to pull them together and to make them dense enough to form a star. That's why it takes millions of years to form a star.
Is there a place where the most amount of stars are born?
Yeah, there's nurseries of stars, of course. Like I said before, there is what we call molecular clouds, and these are the places where new stars are born. For example, in the Milky Way, there's still quite a bit of star formation happening. That's sort of a active star-forming galaxy. And within the galaxy, within the Milky Way itself, most of the gas are closer to the Milky Way center. So for example, the sun is a little bit further away from the center. And that's why there's not so much activity going on. We have some star formation, but it's not as active as regions as close to the galactic center. So usually, if you look at galaxy, most of the star formation happens closer to the center. And then also in these structures, the spiral arms, sometimes you see the picture of very beautiful spiral arm galaxies. And these spiral arms also have more gas and more star formation happening.
You are studying the theories and simulating how stars are born, right?
Yeah, exactly.
So how do you simulate a star being born?
This is a very good question. So despite that it seems like a very foreign concept that doesn't happen on Earth, the physical laws that govern this process is what we're very familiar with. So the gravity that governs the collapse of the molecular clouds is the same as the gravity that governs the apple that falls on Earth. So we know how to write down the equations to describe the action of gravity. We also know the other forces, how we describe them. For example, the movement of the gas is similar to the movement of the gas in the atmosphere on Earth. So we write down all these equations that have different physical components that we are familiar with, and then we put in the conditions that's appropriate for the interstellar medium, for the molecular clouds. For example, the density, the temperature, the gas motion, and we can track how these molecular clouds eventually will evolve and form stars, so that you can solve these equations on the computer. Just like when you make weather forecasts. You put what is the atmosphere condition today, what is the temperature, what is the density, what is the humidity, and then you know physical laws that govern the movement of the gas, and then you can predict to some extent the weather tomorrow, and it's similar. We can model that for star formation.
So do you first see which stars were born and then try to figure out how it was born, or do you just try to predict when the next one will be born?
I think we don't match exactly the conditions for the molecular clouds in our galaxy because it's usually very complex. Hard to say, I match exactly what is the velocity structure, what is the gas density structure. It's likely to be extremely complex and extremely chaotic. So what we're usually trying to study is the statistical properties. Statistically, at what rate the stars form, and statistically what masses the stars form, and how fast they form, and how does that depend on the environment. So it's usually these aspects that we look at in our simulations.
How different is a planet from a star in terms of how it's formed and how you study this formation?
Yeah, the planet, intuitively we know planet doesn't have nuclear fusion, right? The Earth, it has some nuclear decay in the core, it has some geothermal properties, but it's not burning like a star. It's not very hot.
True.
So we know the composition is different. The sun is made of mostly hydrogen and helium. The Earth, it has a lot of rocks, a lot of silicon, carbon, oxygen. And other planets, for example, Jupiter, that's also made more similar to the sun, made of hydrogen, helium, a lot of gas. So this is what we know for the end product. Okay, so there we know that the end product is different, and also the planets usually orbit around a star, or two stars, sometimes a binary star. Usually, it's a hierarchical structure. So you have, for example, the solar system, that there are inner planets and outer planets. So we know that at least the end product is very different. And then we go back to ask a question: what leads to this difference? How they form in different situations? And what we think is that first the star form. And then when the stars form, because the star form from the collapse of these very dense molecular clouds, and basically you have a big ball of gas in the center of this collapse. But when it collapses, it also rotates because there is a little bit of rotation usually in the molecular clouds just from random motion of the gas. So you have a little bit of angular momentum. And then these angular momentum will basically cause rotation. So it's like, you have a figure skater and then she brings her arms in and she spins faster. And this rotation will form a thin disk around the star. So you can imagine it's like an egg kind of. So you have a central object and then you have this thin disk rotating around. It's what we call the protoplanetary disk. And from the name, you would have guessed protoplanetary disk means that it is a disk where planets would have formed in. So after a while, the disk has a lot of material, has a lot of gas, and a lot of dust. And after a while, the dust will climb into each other and form bigger and bigger dust like snowballs. And the snowballs grow bigger and bigger and will eventually form planets. But also maybe some other mechanism, for example, some parts of the disk might have so much gas that it can collapse by itself under gravity and form big planets. For example, perhaps Jupiter formed this way, we're not quite sure. But we think that generally planets form in this structure that we call protoplanetary disk around the stars when the star is born.
How mature does a star need to be until it can get planets?
We are still not quite sure yet. So we now know this has to form within a few million years. Because
short.
these short. That's what we call fast in astronomical time scale. We know that this disk doesn't exist forever. They exist for a few million years. So the planets needs to form before this disk dissipates. And second, now with the powerful telescope, for example, there's a radio power telescope called ALMA, can actually observe these disks directly, and we already see some signatures of planets within it. For example, the planet can create structures within the disks and create rings or gaps from the gravity of the planets. Already see these signatures, and we know that the planet has to be there already. But exactly how early is it? 100,000 years, is 1 million years, or 2 million years? We're still not sure, and then we're still looking for evidence. This is a very new field that we started only to observe these protoplanetary disks in detail in the past 10 years.
Oh, so it's super recent.
It's super recent that we know the birth environment.
And do all stars get planets?
Very good question. We don't think every single star have a planet, but we think most stars do. And many stars have multiple planets. So on average, especially stars similar to our own sun, has at least one planet on average. That doesn't mean every star has to have a planet. It doesn't mean every star has one planet. Some stars maybe have 0, some stars maybe have 10. But if you pick a random star in the sky and ask how many planets are there, there's likely more than one. And this is a big discovery that happened also in the past 20 years or so, that we just realized how common planets are. I think people have been under the impression that the solar system was special, that we have many planets, but we never knew whether there are other planets because they're very hard to see. But only in the past 20, 30 years, we have developed the technology that enable us to see these very, very small objects. And we now know there are so many of them that our solar system is unlikely to be special anymore.
That's a bit sad. I liked our special.
It's still special for us. But for the universe, the sun is a very common star. And then we know stars like our sun often have many, many planets.
Is there a star that is more likely to have more planets than another?
What we are trying to observe with telescope is to pick up different types of stars and ask, with this technique, can we see a planet? However, you have to remember the detection depends on the technique. So for example, for stars that have more mass than our own sun, a lot of the times it's not easy to observe the planets there. These stars have a lot of sunspots or oscillations that they don't look very stable. And if we want to detect the signature of the planet, for example, the planet can transit in front of the star and make a small dip in the light curve of the star, or the planet can drag the star a little bit, so the star moves a tiny bit. So this detection technique usually relies on the stars being relatively stable. So our own sun is a good target, or smaller mass stars. So for now, we know that low mass stars like our own sun is likely to have planets. And the higher mass stars, we don't observe as many planets. But is that because they don't have them? Or is that just because it's hard to find them? I think that's a bit unclear still.
Now coming back a bit more to your research.
Yes.
What do you feel is the most important breakthrough in your field?
Generally speaking, in the star and planet formation field, biggest breakthrough in, say, last 20 years, I think, is that we're able to study the formation of planets. Of course, there are older breakthroughs. For example, we know the composition of stars. That happened more than a century ago. But in most recent breakthrough, I think, is the new observational technique allowed us to observe planets both at the time when they already formed, also at the younger times, at the beginning. And the development of computational powers, so the very supercomputers, allowed us to model these systems in detail, but also we are motivated by the fact observationally we know from the telescope that there's so many planets forming, and they formed already within a few million years of the star formation. So that really gives us a realization that planets are common, the formation is fast, the formation is robust. So we think that planets are not a rare thing. It's not so fragile. It's not like, we have to have a special condition for them to form. But now we know that actually they're pretty common. So I think that's the biggest realization in, say, the past 20 years.
Many times the public has certain misconceptions or wrong ideas about certain fields of science.
Yes.
In your case, even within astronomy,
Yeah.
what is the biggest wrong idea that the general public usually has about your field?
General public, I think for me, I got this impression when people ask what I do. I say I do astronomy or astrophysics, and people are like, wow. And silence. I think people has the misconception that it is a very mysterious subject. Of course, the stars we study, the galaxies we study, the early universe we study are very far away. But I want to stress that they're governed by the same physical laws that we're familiar with on Earth. For example, if you ask somebody who studied the movement of continents on Earth or the movement of air on Earth, they often use very similar tools as we do, because the physical laws that govern these types of processes are, for example, gravity, for example, the movement of gas, the movement of fluids, for example, radiation. And these are the same physical laws that we study in the stars, or in the interstellar medium, or in the galaxies. So I think it's important to remember that we can apply the same physical laws we're familiar with to the astronomical objects and understand them. To me, that's the most interesting part. You'll be surprised, a lot of people will be surprised, actually the tools we use and the methods we used are not so mysterious.
Thank you so much, Munan. This was a great talking with you and understanding a bit more about star formation, planet formation, and all of these super interesting questions about your field. Thank you so much for joining us.
Thank you for having me.
And to everyone, Merry Christmas.
Merry Christmas!
Wherever you are. And enjoy your holidays. Bye.
Bye, thank you.